start. Okay. So I'll state a couple more theorems. Next one is the following. Okay. This series 1 to infinity an converges if and only if this series and from some bigger number to infinity an converges for every integer n. Why is that? What is the difference between these two series? Well, here this is the sum of all the terms from the term starting from 1, a1, a2, and so on. And this is starting from nth term. The difference between them, first and minus first terms, right? And that doesn't make a difference. I mean, the important thing is the infinite part of this series. So no matter what the first terms are, first, let's say 500 terms are, the series will be convergent. Its convergence will be determined by the rest of the series. Okay, so so I can write down proof something like this. If Sn is, let's say, a1 up to an is the nth partial sum of this series, then what is the nth partial sum of the second series? Sn minus Sn, which is a n plus 1 up to an is the nth partial sum of the series. Actually, maybe I should okay, yeah, I should have n minus 1 so that this starts from n of the series n up to infinity an. So one of them has partial sums, this one, and the other one has partial sums, Sn minus n. So for the other one, the partial sums is this, Sn minus. This is the fixed number, right? This is the fixed number. Big N is constant. It is fixed number. Let's say it is K, okay? And you wonder whether these are convergent or not. Well, if this is convergent, then of course this will be convergent. And if this is convergent, then this will be convergent. Because the difference between them is a fixed number. One of them is, let's say, 10 minus the other one, right? So if one of them is convergent, then the other one is convergent. Thus, hence, Sn is convergent if and only if Sn minus Sn is convergent. right? Because this is a fixed number. The first, let's say, 500 terms, the sum of the first 500 terms. Right? The important part of the series, which will determine whether the series is convergent or not, are not the first, let's say, 500 or 5 trillion terms. The important part is the tail of the sequence, that infinite tail. That determines everything. Therefore, the first terms, doesn't make any difference. Okay. Another result about series, if an is ultimately positive, then the series must either converge uh, if the it converges if the sequence of partial sums is bounded, or diverge to infinity. If the sequence of partial sums is not bounded above. So let's see why this is telling us. What this is telling us, we have an ultimately positive sequence, which means that after some point on, all the terms of this sequence are positive. Okay. Uh, so Sn is something like this. I have some terms. These terms could be 0 or negative or positive, but after some point on, let's say the nth term, all of these are positive. Okay. So from the nth term, after the big nth term, so this could be, let's say, 158. After this term, all of them are positive. This means that this Sn is ultimately increasing, because what is the next term? You add another positive term, and then you add another positive term. So Sn is ultimately increasing. Okay. uh, and so yeah, I have this sequence S1, S2, S3. The first terms may not be increasing, because an's could be positive or negative, so it can be like this. But after the nth term, after this term, you are just adding positive numbers each time. Therefore, the sequence will be increasing. And since it is ultimately increasing, so proof, let's say, Sn is ultimately increasing. And when if you have an increasing sequence, then you have two things, right? Two things might happen. If it is bounded from above, it will be convergent. If it is not bounded from above, then of course it means it is going to plus infinity, right? And this is exactly what the theorem is telling us. If you have an ultimately positive, then this series which is the limit of partial sums, either converge if the sequence of partial sums is bounded, or diverge to infinity if the sequence of partial sums is not bounded above. Okay? The book doesn't give proofs for these, and I am not giving you the proofs, but I am just giving you the idea, why these are true. This is not a formal proof, but basic or important parts of the proof. The idea is that if ANs are ultimately positive, then the sequence of partial sums are ultimately increasing. Okay? And an ultimately increasing sequence is basically an increasing sequence, and it is convergent if and only if it is bounded from above. Bunu niye sildim ki? Okay, şu kalsın. Hence, the result follows. Okay, there is this theorem also, which is important in practice. If AN and let's say another series Bn converge to A and B respectively, then we have the followings. First statement is that C times AN, this is converges to C times A, where C is any constant. C is any constant. AN plus or minus BN converges to A minus B, or so A plus B or A minus B. If you have plus, then it will converge to A plus B. If it is minus, then it will converge to A minus B. And if AN is less than BN for all N, then the limit also will be less than that number. That's also something very easy. Let me just, look at the first or the second one. So here you see, A is the sum of this, right? So if Sn is the nth partial sum, then the limit of Sn is equal to A. And B is the sum of the second sequence, Bn. And let's say sum of partial sums is Rn. So it is B1 up to Bn, and limit Rn is equal to B. So for the sequence An plus Bn, what is the nth partial sum? The nth partial sum of this series is what? It is A1 plus B1 up to an plus bn. Well, this is just Sn plus Rn, right? Sum of the first n A terms and sum of the first B terms. So, and what is the limit of this? The and partial sum has limit. What is that limit? Well, this has limit A, this has limit B. Therefore, the sum has limit A plus B. So the sequence of and partial sums is convergent and the limit is A plus B. Therefore, an plus bn and from 1 to n is equal to A plus B is convergent. Okay. The rest are kind of similar, so it's enough if I just do this much. Let's do some examples. Uh, let's, for example, look at this one. 1 plus 2 to the power n plus 1 divided by 3 to the power n. Well, what is this? I can write this as 1 over 3 to the power n plus 2 times 2 over 3 to the power n, right? Uh, this series is convergent. It's a geometric series, and the second one is also convergent. And you are just adding these two series. Well, the sum will be convergent, and the limit or the sum of the two series will be just sum of the values of those sums, individual sums, right? So I can write it this way. This is just 1 over 3 to the power n. And then here, you see I have this 2 times this. And here I can just take this constant out. Right? Here, you see here we had this also. If an the series an convergent, then c times an is also convergent, and the limit is just c times a. So you can just take this c outside the summation. So here, this is just equal to this. I can do this because all these series are convergent, right? These are geometric series where r is 1 over 3 and 2 over 3. So both are geometric series with r 1 over 3 and r 2 over 3. Both of them are less than 1. Therefore, this is just 1 over 1 minus r plus 2 times 1 over 1 minus r. R here is 1 over 3, but here it's 2 over 3. So this is just 3 halves plus 2 times 3 over 1. So it is what? 6 and then 1,5 daha 7,5. Ne diyor? 15 mi? 15 over 2. Alright. Yanlış yapmışım ama nesini yanlış yaptık? Oh, okay. This starts from not 0 but 1. Sorry. Yeah, you have to be careful. This is not starting from uh, or you should have here n minus 1. You can do that by doing this 1 over 3 times. I take one of the 1 over 3 outside, so 1 minus 1 over 3 n minus 1 plus 2 times 2 over 3 and then 2 over 3 n minus 1. Okay, and then I can do that. So this is just 1 minus 1 over 1 over 3 plus this is just 4 over 3 times 1 over 1 minus 2 over 3. All right. Nedir bu? Ee, 1 bölü 3 çarpı burası 2 bölü 3 oldu. Yani 3 bölü 2 olacak. 4 bölü 3 çarpı burası da 1 bölü 3 yani 3 bölü 1. Nedir bu da? 1 bölü 2 artı 4. Yani 9 bölü 2. Okay, now it's correct. Sorusu olan var mı? Any questions so far? Next, we have some tests which tells us whether a given series is convergent or not. Unfortunately, we don't have a universal test which tells you any sequence is convergent or divergent. Okay, which works for all the sequences. We have tests which work for some sequences and which doesn't work for some other sequences. And for those sequences, if one test doesn't work, then you look for some other tests, okay, to check convergence. As I said, we don't have an ultimate test which works for all the series. Okay. The formula for so we had this. If n starts from 1, this is equal to a times 1 minus r, provided that, of course, r is less than 1. But here we had not n minus 1, but n. Okay, n. So I have to first write it as n minus 1. The thing is the following. You see, if you look at this, let's say 1 to infinity, 1 over, let's say, 4 to the power n. What is this? This is 1 over 4 plus 1 over 16 plus 1 over 64 and so on. This doesn't start from 1. It starts from 1 over 4. So I can write it this way. If I take 1 over 4 parentheses, then I will get 1 and then 1 over 4, 1 over 16 and so on. And now that is equal to 1 over 4 times this is 1, 1 over 4 and so on. So that is just 1 minus 1 over 4. Okay. 1 over 4. This is 3 over 4. So 4 over 3. So this is just 1 over 3. Okay. So if you don't have n minus 1 here, you cannot right away say that this is just 1 over 1 minus. If you remember the formula for power series, we had this geometric series. I had a times r to the power n minus 1. Okay. All right. Now, as I said, we have now convergence. So this is section 9.2, not 9.2, 9.3. Convergence tests for positive series. The first one, the integral test. Actually, we already used the integral test for the harmonic series, right? I had a series, the harmonic series. For the convergence of that test, I considered it's a graph, and we write down a function. We compared the areas of rectangles and area under the curve and so on. That was actually the integral test. Now we will see it in a more general form. Here is the theorem, which we used without stating it. Suppose that an is equal to f of n, where f of x is a positive, continuous, and non-increasing function on some interval like this for some positive integer n. Then uh, I have this series an, and I have this integral. This is a series. It may be convergent or divergent. This is an improper integral. I have a continuous function, but the interval is unbounded, right? It's from n to infinity. So this integral could be infinite also. The statement is that they either both converge or both diverge, okay? So if one of them is convergent, then the other one is convergent. If one of them is divergent, the other one is divergent. Then uh, both converge or both diverge. Diverges to infinity. Yani ikisi beraber convergent veya ikisi beraber sonsuza gidiyorlar. Neden? İspat gayet basit. Proof is just the same as the one we used while we are discussing the divergence of the harmonic series. Okay, now Sn is the nth partial sum. A1 up to A2 up to An. Okay. And choose n larger than Sn. Okay. For the series to be convergent, Sn should have a limit, right? Sn should have a limit. Now, you see that this Sn can be written like this. This is Sn and then an plus 1 up to an, because this Sn is the sum from a1 up to an, and the rest is an plus 1, an plus 2 up to a small n, assuming that small n is bigger than big N. Okay. But you see, this is just Sn, and this is f of n plus 1, and so on, f of an, no, not an, f of n, right? Because by assumption, Sn and Fn are the same if on this interval. So if n is larger than big N, then instead of an, I can write f of n, okay? They are equal on this interval, meaning that this n should be at least this big N. Yani serinin ilk terimlerindeki a'lar f'e eşit değil. Ama belli bir yerden sonra diyelim ki ilk 500 terimi atın, geri kalanında a'n'ler f of n'e eşit. O zaman bunu yapabiliyorum. O yüzden ilk n terim için bir şey yapmadım ama sonrası için bunu yazabilirim. Şimdi burada ne var? Bunu şöyle yazabiliriz. Bu Sn plus sum of the areas of rectangles shaded. Şimdi ben size resim çizeyim. Şuradaki rectangle'lar. Şimdi şu n'e kadar bir şey yapmıyorum. F nasıl bir fonksiyondu? Azalan, continuous ve değerleri de şeye eşit. Yani şurada n plus 1 var. Şurada n var. This is just f of n, so this is a n. This is a n plus 1, and this is a n, right? The values of f are equal to the values of a n, sorry. And here I have this rectangles like this. What is the area of this rectangle? Well, height is okay. Bunu n'den değil de şeyden başlatmak lazım belki. n-1'den ya da yok. N'den başlatırsam şu rectangle'a bakacağım. Bir dakika. Şu rectangle. An is this, but I have fn plus 1. Fn plus 1 is this area. Okay. So it is this one. Smaller rectangles. Not bigger ones, but smaller ones. Right? This is an, but I am interested in an plus 1. An plus 1 is the area of this rectangle. An plus 2 is the area of this rectangle. Right? So this is an plus 1. This is an plus 2, and this is an. So sum of these rectangles is equal to this sum of values of the function f. And what can we say then? So Sn, right? This Sn is equal to Sn plus the area under the curve. The area under the curve is what? N to infinity f of t dt, right? The area under the curve is integral of f of t from n till infinity. Okay, so if this is convergent, then this is a finite number. This means that this Sn, little sn, cannot be bigger than this number. Therefore, this Sn is bounded from above, but it is increasing and bounded from above. Therefore, it has to be convergent, right? So if is convergent, then this Sn is bounded above and thus convergent. Why is that? Because Sn is a sequence of partial sums of a sequence of positive terms, right? An's are all positive. So Sn is increasing because Sn plus 1 is always larger than, so Sn is increasing. Since it is a monotone sequence, it is increasing. If it is bounded from above, then it has to be convergent. And if it is convergent, then the series is convergent. Hence, the series convergent. For the other direction, if the series convergent, then we have what? Then consider the diagram below. Bu sefer de şu resme bakalım. Almost the same picture, but slightly different. Okay, so I have this function again, n plus 1. Here, n minus 1 and n. Let's say this time I look at this rectangles. This value here is just a n, right? This is just a n plus 1 and so on. So the area of this rectangle, is a n. The area of this rectangle is a n plus 1. The area of this rectangle is a n minus 1. Yes. So Sn, which is just S1 up, no, not A1 up to, let's say, n plus 1 up to n. This is just Sn. And then sum of this, okay, maybe I include also this an here. Okay, let me write this way. Plus an plus 1. What is an plus 1? It is the area of this rectangle, right? An plus 2 is the area of this rectangle. This, let's say, up to go an. So an. Yes, this is the area of this rectangle. But you see, this time rectangles are higher than the curve, right? So some of these areas, starting from n plus 1 up to here. So this rectangle, this one, and this one, the sum of these rectangles is larger than the area under the curve. So, okay, here uh, some of areas of the rectangles shaded, but that is larger than the following: Sn plus 1 plus area under the curve, starting from where? N plus 1 up to infinity f of t dt. Okay. Now you see, I assume that my series is convergent. If this is convergent, then sum of partial sums is convergent. Therefore, this is convergent. But we know that any sequence which is convergent is bounded, and therefore is bounded. Therefore, this thing is bounded. This is always, of course, positive. Everything is positive, right? I have an object which is less than a fixed number. So this thing is bounded. This implies this integral is bounded. But f is a positive function. If you have a positive continuous function so that its integral from a fixed number till infinity is bounded, then that improper integral has to be convergent, is bounded, and thus it is convergent, because f of t is a positive sequence. Okay, not sequence, function. I mean, pozitif bir fonksiyonun sıfırdan veya işte belli bir sayıdan the integral of a positive function from a fixed number till infinity is convergent if and only if it is bounded. Okay, and here it is bounded because this is bounded, and it bounds the integral. Okay, so that proves the integral test. We have already seen one example. Let's give another example. This is called p-test. So the conclusion is this: n from 1 to infinity, n to the power minus p, which is just summation from 1 to infinity 1 over n to the power p. This is converges if p is greater than 1, diverges to infinity if t is or equal to less than 1. Why is that? We can just use solution or proof. Just use the integral test. How can we use the integral test? Well, let f of x to be the function 1 over so x to the power or 1 over x to the power p, okay, for x positive, then f of n is just 1 over n to the power p, which is an, right? And this function clearly f of x is continuous, right? This is a continuous function, continuous, and it is decreasing. It is decreasing. Why is that? Just compute its derivative. What is the derivative of this? Derivative of this is just minus p times x to the power p plus 1, right? For x is positive, this is a positive number, but here I have minus p, so this is negative. Okay. Here, of course, p is a positive number. P is positive. Yes. But we wonder whether this is convergent or not, and it depends whether this positive number is greater than 1 or less than 1. We don't take negative powers. If you have negative powers, then it will be divergent right away. Maybe we can discuss it later, that part. But right now, let's assume that p is a positive number. Therefore, this is negative. Derivative of f is negative. Therefore, it is decreasing. Okay. And then what is the integral of this gadget? F of t dt. Well, this is minus p over t to the power p plus, yok nereden çıktı o ya? 1 over x to the power, no, t to the power p dt, right? What is this integral? If p is less than 1, so if p is less than 1, then this is, no, greater than 1, sorry, greater than 1. This is just what? T to the power ne olacak bu? P artı 1 olacak değil mi? 1 bölü eksi P artı 1 mi? Bu T üzeri eksi P artı 1 türevini alırsanız aşağı inecek. Bunu cancel edecek. Tamam. N sonsuz. What is this? If bir dakika. Yok. Eksi P 1 arttırıyorum. Şurası P eksi 1 olacak. Özür dilerim. Burası da P eksi 1. Okey. But if p is larger than 1, then uh, p minus 1 is still positive, right? Therefore, I have t to the power something positive. If you have t to the power something positive and let t go to infinity, then denominator will go to infinity. And if denominator goes to infinity, this thing will go to 0. So when you plug infinity, actually you don't plug infinity, you plug, let's say, r, and you let r go to infinity, this thing will go to 0. So this will be 0 minus, you plug n. When you plug n, I have another minus, so it will be plus 1 over p minus 1 times 1 over uh, n to the power p minus 1. But this is a finite number, so that this integral is convergent. Is convergent. But if this is convergent, by our integral test, the series is convergent. Hence, by the integral test, the series is convergent. We have to also consider the case where p is less than or equal to 1, but let me do it later. Case 2, p is less than or equal to 1 and positive. Okay, so this is the case where p is larger than 1. If it is larger than 1, then it is convergent. And that was our actually claim, right? This is convergent if p is larger than 1, divergent if it is less than or equal to 1. I did half of it. We will do the other half next time. Sorry, I took your 5 minutes. Let me stop.